Hi class, these are some notes for chapter 2. I didn't record the Zoom because I was playing around with the other video system and then forgot to start Zoom. So I'll spend 10-15 minutes going over chapter 2 for you, okay? So chapter 2 is about building a simulation model, and the model that I had, or one of the models we had, was this single tank which could fill up with water. Okay, and it had a faucet at the top bringing water in at a rate of Q1. Okay, at a rate of Q1, and then it emptied at a rate of Q2. Okay, and the idea was to build a model of this system. A couple of things we know is that the cross-sectional area of the tank, so we'll assume the tank is cylindrical and has a cross-sectional area of A. Now, the other thing we can assume is that there's conservation of mass, okay, between the water coming in and the water going out. So that means we can write down a differential equation that tells us the rate of change of volume in the tank must be equal to the amount of water coming in minus the amount of water leaving. And the units for these will be volume per unit time. Okay, so the volume per unit time. So I can, if I take the difference between Q1 and Q2, that'll give me the rate of change of the volume in the tank. Now, the state variable is going to be the height of the tank, of the water in the tank. And so what I really want is a differential equation that describes the rate of change of the height of water, okay? So, but I've got only the rate of change of volume, so I need to do some conversion. Now I know that the volume is the cross-section area times the height, because I'm assuming the tank is a cylinder. And if I differentiate that, I get dV by dt equals A times dH by dt. Now, A, of course, is the cross-sectional area. That's fixed, so that's a constant. So that's why this differentiation works like that. Of course, I can now substitute this into there. So I end up with, and if I divide both sides by the area, I get dH by dt equals Q1 minus Q2 divided by the area. Okay, so now I've got the differential equation in terms of the height. That's good. Q1 is a constant. Okay, so this is a constant. Okay, in this model anyway, it's a constant. But I need to do is decide on Q2. Now there are various things I can do here, but the easiest one is just to assume that Q2 is directly proportional to the height. Okay, that works if the water flow is relatively slow. So that's what we'll assume. In which case, if it's proportional, then the flow must be equal to some constant, which I call K1 in the book, times the height. Okay, so I can now rewrite my differential equation. dH by dt equals Q1 minus K1H over A. Okay, and that's my differential equation. Okay, now a couple of things worth pointing out here. We've got at least three types of quantities here. We've got H, which is a variable. In fact, we're going to call that a state variable. Okay, state variable. I have things that are coming in or things that I can change, such as Q1. That'll be an input to the system. That's the only input to the system. It's the only thing I'm going to be able to change. I can't change the cross-sectional area, for example. I can't change the width of the pipe coming out. And then there'll be constants, and the constants include the cross-sectional area and this constant related to the pipe coming out. I'll call those parameters. In principle, I could change them, but I'm not going to. The other thing is, of course, there's acceleration due to gravity, okay? That's another parameter, but I can't change that at all. So these are the four different kinds of quantities we see in this model. And these in any model you'll find these kinds of quantities. So let's expand this model and move on to a bigger one. Let's do a 2-tank model, because that's the next model that's given in the book. It starts off with the first model, 1 tank, and then just adds a second tank. Okay, and the second tank has another flow of water coming in, which is Q4. Okay, and the water leaving is now called Q3. There are 2 heights. Okay, there are 2 heights. Let me just reduce the size of this. Is this better? There are 2 heights. Maybe that's too thin. There are 2 heights, H1 and then it's H2. Okay. There are 2 Ks, K1 and K2 for each of the tanks. And we'll assume that they both have the same cross-sectional area, okay? I mean, they could be different cross-sectional areas, but we'll keep them the same. So now I need to write down the differential equations for dH1 by dt and dH2 by dt. Now the dH1 by dt actually will be exactly the same as the 1-tank model, which was Q1 minus K1H over the cross-sectional area. It's exactly the same, actually the same one. Now for the second tank, however, I've got a couple of things happening. I've got two things coming in and 1 thing leaving. So I'm going to have 2 terms, 2 positive terms, which is going to be K1 H1, that should be 1, okay, plus Q4, that's all the water coming in. And then I need to subtract from that the water leaving. In fact, let me just change that straight away to, I'll put it in a different color, minus K2 H2. And then I divide the whole thing by H. By A, the area, okay? That's the model. This is now the complete model. That should be 2. That's a complete model now for the tank system. And again, if you look at this, you'll see the same kinds of things. You'll see the state variables, H1, H2. You'll see 1 input, Q1. You'll see, let's pick another color. You'll see a couple of constants, K1, the area, and K2. And I think that's it. All right. Okay, so there's 2 examples of models. And so let's talk about these different kinds of quantities. The first one was a state variable. So these are the variables you'll find on the left-hand side of the differential equation, okay? So if you've got a model with, say, that needs 5 differential equations, then you'll have 5 state variables on the left-hand side of the differential equation. I'll just call it ODE, okay, for ordinary differential equation. Traditionally, these variables are given the symbol x and indicated as a function of time because this variable can change in time, okay? The other one that we have are the inputs. Now these are things that are coming into the model that we have control over. And the tank model, these were, well, there's only one. That was the amount of water coming into the first tank. But there could be any number of inputs. Actually, I'm wrong. Sorry, I'm wrong. Of course, there was another input, which was Q4. Okay, so Q4 was also an input. All right. These things, these inputs, are things that I control. So these are quantities that you control, okay, directly. Right? So, and traditionally these are given the symbol U of t. Notice also they're a function of t because there's nothing stopping me for having the rate of water coming into the tank varying with time. Okay, so perhaps maybe I would start the water off low, just say Q1, and it would slowly rise linearly. Okay, I could have that, and that would be my UT. okay? But often we'll just assume a constant value. The other one are the parameters. Parameters, fixed quantities, okay? And there's two types of these. There are either ones that I could in principle change, and therefore if I do change them, they turn into inputs. But I don't. But I've decided not to bother changing them. I'm not interested in them, or maybe they're just too difficult to change. For example, in the case of the tank model, I'm not going to bother having lots of tanks with different cross-sectional areas. That might be too expensive and so on. Okay, but I could imagine changing K1 perhaps if there was a tap on the end there. I could turn the tap and change the diameter of that outflow. In that sense, I could change K1. But if I'm not changing it, it gets relegated to a parameter. Okay. The other ones that are part of the parameters are also absolute constants, such as the force of gravity, things like that. And the other fixed quantities, I could give you some other ones, is, for example, the temperature. That's another one, okay? And you can give these the symbol. Often the books don't distinguish parameters. They will just use some symbol like Greek letters or something, but I tend to use the letter P. Now, these are not a function of time. Okay, so there's no function of time here. These are absolutely fixed, do not change at all. All right. Now, there's one other thing that people often also discuss, and we don't really have this in these models, but outputs. Okay. These are things, quantities we actually observe. Okay, you may have state variables in your model that you don't actually can't observe, or the way you observe them means they're not exactly proportional to the state variable itself. That doesn't happen perhaps too often, but for example, when I'm measuring the height of the water, I'll be using some kind of ruler here, some straight edge, right, with little divisions on. I'll be perhaps measuring the height using some straight edge. So I'm not actually measuring the height directly. I'm comparing it to a straight edge, and then I'm looking at the straight edge. So the straight edge is effectively a proxy for the actual height. And then this is called an output. This is the thing that we actually observe. Okay. Now, we won't be dealing with outputs much in this class, but they do exist, and they are quite important. It varies from problem to problem. In biology, for example, we often don't measure the thing directly at all. For example, a protein concentration, we'll measure it as a fluorescence or a stain on a gel. We never actually measure the protein directly, so they're always proxies. Now, symbolically, these are often indicated with the symbol YT. So those are the outputs. So those are the three kinds of quantities that we have. All right. So I think I'll stop here, and I'll then start a new video in a minute.